So one of the most important concepts or ideas for studying linear time-invariant systems is the so-called impulse response. And the physical idea here is that an impulse is a very short, discontinuous signal that models, for example, striking a pool ball with a cue or a bouncing ball or something like that. So it's a sort of a signal that transfers energy in zero time, basically. Now, mathematically speaking, we can't really make up a function that's zero everywhere except at one point, but still, say, integrates to something non-zero. There are ways around that, and to do this in a mathematically rigorous way, we would have to do something called distribution theory. I'm not going to do that, at least not in this video, so I'm going to keep this on a more elementary level. And in order to do so, we need to introduce a little bit of terminology. So the first thing is that we're going to look at a rectangular pulse. So that's an input signal that's zero most of the time, but during a short time interval starting at equals zero, it's large. So we're going to choose a variable called delta, which is the width of the interval where the signal is non-zero, and the height of the signal or the intensity of the signal is chosen so that the integral of p delta equals 1, so the area under the curve should be 1. So we have a function that's 0 everywhere except when t is between 0 and delta, where the function value is 1 over delta. So at the bottom left corner you see a graph p delta. Okay, and what do we want to do? Well, we want to let delta tend to 0. And as a function, or as a sequence of functions, these p deltas don't have a usual limit as delta goes to 0. But it turns out that if you have a linear time-invariant system, then most of the time the corresponding system's responses actually do have a limit. So if you use one of these p deltas as an input signal to our system, and we try to measure what happens as delta tends to 0, then under fairly mild assumptions on the system, the corresponding output values will actually have a limit as delta goes to 0. And that limit is called impulse response to the system. And I'm not going to worry about exactly what kind of assumptions we have to put on the system S in order for it to have an impulse response. All the systems you will ever encounter satisfy those conditions. And as I mentioned in passing, if you know a little bit of something called distribution theory, this can be made more mathematically precise. In the setting of distribution theory, these p deltas themselves have a limit as delta tends to 0, but the limit is not a function, but it's an impulse or something called the Dirac delta distribution. Anyway, let's look at some examples. Or maybe to make things a little bit easier, before we do the example, let's introduce one more thing. So the function theta t, which is 1 for positive t and 0 for negative t, it doesn't really matter what value we put at t equals 0 itself. That function is called a unit step, or maybe more commonly Heaviside step function. And the physical meaning of this function, so this is sort of a mathematical model of flipping an electric switch. And the point is that the system response to theta is often easier to measure than measuring the impulse response itself, because To measure an impulse, the impulse response directly, we would have to send through, well, to get an approximation to the impulse response, we would have to use as an input signal one of these p deltas where delta is very small. The problem is that if delta is very small, then the intensity is very large, even though the intensity is put through the system through only at very short period of time. But nevertheless, if this system is, for example, an electric circuit, and we try to hit it with an extremely high voltage over a short period of time, we would probably fry the circuit. So the impulse response itself is often very difficult to measure, whereas the step response, the system response to the unit step, is often a lot easier to measure. It just, we have so let's again take the electric circuit as an example. Then the step response is just measuring what the system does when we flip a switch, turning on the voltage. Okay, so let's do an example. Let's say that we have a linear time-invariant system. Of course, in practice, how do we know that? Well, sometimes we can make such assumptions by measuring the system response to a few cleverly chosen in signals, or perhaps more commonly that this system models some kind of natural phenomenon that we expect to be linear time invariant. So anyway, let's say that we have such a function, such a system, and we measure the unit step response, and it turns out that the unit step response looks like the graph in the middle of the picture here. So at t equals 0, we turn the switch on, and the output signal will then increase linearly from 0 to 1 in 1 second, and after that it will be constant 1. So how can we use this information to compute the system's impulse response? Well, actually, it's not as difficult as you could, as you might imagine. And all we have to do is use linearity and time invariance of the system. Let's see how it's done. So the first observation is that if you take the Heaviside step function, theta of t, and we subtract, say, theta of t minus 1, that will be the function on the top here, theta, and the next picture is theta t minus 1, which is just the time delayed theta, of course. And if we subtract those two graphs from each other, we see that, well, to the left of equals 0, it's just 0 minus 0. When t is between 1 and 0, then theta is 1 and theta t minus 1 is 0, so then they're 1 minus 0, so 1. But when t gets larger than 1, then both of these terms by themselves equal 1. So when we subtract, we get 0. So that means that the unit rectangular pulse P1 is just theta t minus 1, as in the picture here. And by using time invariance and linearity, we know that the system response to this P1 is then the system response to theta minus the system response to T1 theta, the time delay theta. That's linearity. And the system response to T1 theta is T1 of the system response to theta. That's time invariance. So that means that we can compute the system response to theta, well, that was given, and we can compute the time delayed system response to theta. It's just a time delayed unit response. And the difference between these two pink graphs on the bottom of the page is the system response to P1. So the system response to P1 here would be some kind of triangular pulse. Okay, oops, sorry. And more generally, if you look at P delta, well, it looks pretty much the same. P delta can be written as theta of t minus theta of t minus delta, but then we also have to normalize by this factor 1 over delta to get the right height. And if you try to do this now for our example, then of course S of theta is still the same as it was. If you translate the impulse or the unit step response by delta, we get just a corresponding function translated delta steps to the right. And if we subtract those two, well, then we get something that looks like the rightmost picture here. If t is negative, you just get 0. If t is between 0 and delta, well, S theta starts to rise, and the translated S theta is still 0. So there we get a constant increase. So for t between 0 and delta, we get an output that grows from 0 to delta. And after that, all the increase in S theta is cancelled by the corresponding increase in t delta S theta, and we get a constant plateau here all the way up to 1. But when we pass 1, of course, then S theta will cease to increase, whereas t delta S theta still increases a little bit, so we get the difference will be decreasing all the way up to t equals 1 plus delta, and after that, both of these two signals we are playing with, we go to 1, and when we subtract, we get a 0. Now, this is just S theta minus t delta S theta, and then we also need to multiply with 1 over delta, which rescales the y-axis, and we get something that looks like the picture at the far bottom of the page. And this will be the system response to p delta. And we can see here now that when delta tends to 0, what will happen is that this interval where the function increases will be shorter and shorter, and correspondingly the interval where the output then decreases again will also get shorter and shorter. So in the limit as delta tends to 0, what we get is just a function that looks like this: 0 as t is negative, 1 when t is between 0 and 1, and again 0 when t is bigger than 1. And that must be the system's impulse response. And if you try to look at these calculations and do them in a more abstract or more general manner, you can convince yourself that the impulse response will actually be the derivative of the unit step response. Now, in order for this to work, we need to take the derivative in what's called distributional sense. The problem here is, of course, that the given unit step response is not a differentiable function. But everywhere where the function is differentiable, there the derivative is the impulse function. Again, this can be made more precise using the language of distribution theory. Okay, let's finish this off and continue with properties of the impulse response in the next video.